Quantum physics has long been a magnet for mystery, speculation, and myth. Ever since pioneers like Einstein, Bohr, and Heisenberg shook the foundations of classical physics, the public imagination has been captivated, and sometimes misled, by what quantum mechanics suggests about the nature of reality. At the heart of it all lie principles that defy our everyday intuition: particles existing in multiple states at once, entanglement that links objects across vast distances, and uncertainty that limits what we can know. But amid these marvels, many misconceptions have taken root. One of the most persistent myths is that quantum mechanics proves human consciousness can control reality. This idea often springs from misinterpretations of the observer effect, which states that the act of measurement can change the outcome of an experiment. While it's true that measuring a quantum system can collapse its wave function, this doesn't mean human intention shapes reality. Rather, it's about physical interaction, regardless of whether a conscious observer is present. Another widespread myth involves quantum entanglement, sometimes called spooky action at a distance. Many believe entanglement allows faster-than-light communication or teleportation. In reality, while entangled particles do influence each other's states instantaneously, no usable information travels between them faster than light. Entanglement doesn't break the laws of causality or allow sci-fi-style messaging across galaxies. The idea of quantum healing is also a frequent misrepresentation. Some alternative medicine practitioners claim that quantum mechanics can explain miraculous cures or energy fields around the body. But quantum effects dominate only at subatomic scales, and there's no scientific evidence that they play a meaningful role in biological healing at the macroscopic level. Invoking quantum buzzwords often adds a veneer of credibility to pseudoscientific claims without grounding them in real physics. Even Schrödinger's cat, the famous thought experiment, is often misunderstood. The image of a cat being alive and dead at the same time is not meant to suggest that macroscopic objects literally exist in superpositions. Rather, it was Schrödinger's way of illustrating the absurdity of applying quantum rules to everyday objects without accounting for decoherence, the process by which quantum superpositions break down in large systems interacting with their environments. Quantum tunneling, too, has inspired myths, especially in pop culture. It's true that particles can tunnel through energy barriers they classically shouldn't be able to cross, but this doesn't mean a person could walk through walls. The tunneling effect applies at the scale of electrons and atoms, not at the scale of humans or cars. Even the notion that quantum mechanics inherently supports a multiverse is often exaggerated. While some interpretations, like the many worlds interpretation, suggest parallel realities, these ideas remain speculative, and quantum mechanics itself doesn't demand them. The multiverse is a hypothesis, not an established outcome of quantum theory. Perhaps the most beautiful aspect of quantum mechanics is not its strangeness, but its predictive power. Despite its weirdness, quantum theory is the most precisely tested framework in physics, with applications ranging from semiconductors and lasers to quantum computing and cryptography. It's a reminder that nature doesn't care about our intuitions, and sometimes, truth is far more fascinating than myth. Another captivating element of quantum mechanics is superposition, the idea that particles can exist in multiple states simultaneously until measured. This concept often sparks the myth that our thoughts or decisions can influence which reality becomes real. In truth, superposition is a mathematical description of probability distributions, not an open invitation for the human mind to reshape physical events. The collapse of the wave function upon measurement is a natural process, not a conscious choice. Quantum randomness is another source of confusion. People sometimes interpret it to mean that the universe is fundamentally chaotic or unpredictable. While quantum events do contain inherent randomness, like the precise moment when a radioactive atom will decay, this doesn't translate into disorder at the human scale. On the contrary, large-scale systems often behave predictably because countless random events average out into statistical regularity. This is why we can build functioning computers, predict chemical reactions, and send spacecraft to distant planets despite the quantum chaos beneath. Entanglement has also inspired claims about universal oneness or cosmic consciousness, the idea that because particles can be entangled, everything in the universe must be interconnected in some mystical way. While this is a poetic notion, it stretches the physics far beyond what experiments support. Entanglement is a measurable, temporary condition between well-defined systems, not a universal glue binding all things at all times. Another misconception lies in the idea that quantum mechanics defies causality. While quantum events can be non-deterministic, they do not allow effects to precede causes or permit violations of time's arrow. Quantum correlations do not transmit usable signals backward in time, they only reflect deep statistical relationships. Causality still reigns supreme, even in the strange world of quarks and leptons. In the realm of technology, quantum computing is frequently hyped as a magical solution to all computational problems. While quantum computers hold immense promise, particularly for specific tasks like factoring large numbers or simulating quantum systems, they are not omnipotent machines that will instantly crack all encryption, predict the future, or solve every unsolved problem overnight. Much of their potential still lies in early research, and engineering practical quantum hardware remains a monumental challenge. Perhaps one of the most persistent myths is that quantum mechanics completely overthrows classical physics. In reality, quantum mechanics refines and extends classical laws, and in everyday conditions, classical physics remains an excellent approximation. When you drive a car, throw a ball, or fly a plane, Newton's equations work beautifully. Quantum effects become noticeable only under extreme conditions, very small scales, very low temperatures, or very high precision. At its heart, quantum mechanics teaches humility. It reveals a universe where certainty dissolves into probability, where particles dance on the edge of knowability, and where nature's laws operate according to rules stranger than fiction. Yet instead of descending into confusion, physicists have harnessed this strangeness to uncover deeper truths, construct revolutionary technologies, and expand the boundaries of human understanding. One of the most striking scientific facts about quantum mechanics is its experimental success. The predictions of quantum theory have been confirmed to astonishing precision, in some cases, to more than a dozen decimal places. For example, the magnetic moment of the electron, measured in laboratories, matches theoretical predictions from quantum electrodynamics, QED, with mind-blowing accuracy. This makes quantum theory one of the most successful scientific frameworks ever developed. Another remarkable fact is that quantum mechanics underpins modern electronics. Without the quantum understanding of semiconductors, we wouldn't have transistors, and without transistors, there would be no computers, smartphones, or the internet. Quantum principles also govern how lasers work, how GPS systems achieve their precision, and how magnetic resonance imaging, MRI, helps doctors visualize the human body. Quantum tunneling, while mysterious, is a real, measurable process used in technologies like the Scanning Tunneling Microscope, STM, which allows scientists to see and manipulate individual atoms on surfaces. Without tunneling, nuclear fusion in stars, including the Sun, would not occur, and life as we know it wouldn't exist. A fascinating fact about entanglement is that it's not just theoretical, it's been repeatedly observed and verified in laboratories around the world. Scientists have entangled photons, electrons, atoms, and even small groups of molecules. In recent years, they've even entangled tiny mechanical oscillators. This has opened the door to quantum cryptography, which promises ultra-secure communication using entangled particles to detect eavesdropping attempts. Quantum mechanics also explains why atoms are stable. Without quantum rules, the electron in a hydrogen atom would spiral into the nucleus in a fraction of a second, and matter as we know it would collapse. But because of the Heisenberg uncertainty principle, the electron can never have both a precisely known position and momentum. This keeps it smeared out in a stable orbit around the nucleus. In quantum computing, qubits can exist in superpositions of 0 and 1, unlike classical bits that are either 0 or 1. This opens up new ways of processing information, enabling parallel computations that could dramatically accelerate certain tasks, like factoring or database searches. Yet quantum computers also face challenges, such as error correction and decoherence, which scientists are racing to overcome. Finally, a stunning scientific insight is that quantum mechanics doesn't just apply to small systems, it is universal. Even the vast structure of the cosmos was influenced by quantum fluctuations in the early universe, which seeded the galaxies and clusters we observe today. The fingerprints of quantum physics are thus written into the very fabric of the large-scale universe. Another fascinating fact is the phenomenon of quantum decoherence, the process that explains why we don't see quantum superpositions in our everyday world. While particles at the microscopic level can exist in multiple states at once, interactions with their environment, like air molecules, photons, or vibrations, rapidly destroy these delicate quantum states, making the system behave classically. This is why you never see a baseball spread out across many locations or a cat in a quantum superposition. One of the most revolutionary achievements in modern physics is the experimental violation of Bell's inequalities. This confirmed that nature is non-local in a quantum sense, meaning that no local hidden variable theory can fully explain the correlations between entangled particles. Experiments by Alain Aspect and others in the 1980s, and later loophole-free tests in the 2010s, have shown that the quantum world truly defies classical intuitions about locality and determinism. The Heisenberg uncertainty principle is another foundational fact of quantum physics. It tells us that there's a limit to how precisely we can simultaneously know certain pairs of physical properties, like position and momentum, or energy and time. This isn't due to technological limits but a fundamental property of nature. The quantum world is inherently fuzzy, and precision in one property comes at the cost of fuzziness in the other. A mind-blowing application of quantum mechanics is quantum teleportation. Though it doesn't involve the Star Trek-style beaming of people or objects, quantum teleportation allows the transfer of a quantum state from one particle to another over long distances, using entanglement and classical communication. This has been demonstrated across kilometers on Earth and even between ground stations and satellites, paving the way for future quantum networks and ultra-secure communication. In cosmology, quantum mechanics played a central role in the early universe. Tiny quantum fluctuations during the inflationary epoch were magnified to cosmic scales, seeding the density variations that eventually formed galaxies, stars, and planets. Today, we see the imprint of these ancient quantum fluctuations in the cosmic microwave background radiation, the afterglow of the Big Bang, mapped with exquisite precision by satellites like Planck. A surprising quantum effect in chemistry is the ability of particles to tunnel through energy barriers in chemical reactions, which speeds up processes that would otherwise be too slow at biological temperatures. This is critical in enzymes, where quantum tunneling helps catalyze reactions essential for life, making quantum physics a hidden player even inside our bodies. Finally, quantum mechanics also sets the ultimate limits of measurement and information. Concepts like the quantum limit in amplifiers, the standard quantum limit in precision measurements, and the no-cloning theorem, which says you can't perfectly copy an arbitrary unknown quantum state, are all vital in quantum technology development. They define both the power and the constraints of future quantum devices. Another remarkable fact is that quantum mechanics provides the explanation for why the sun shines. Inside the sun, nuclear fusion turns hydrogen into helium, releasing enormous energy. But classically, the protons in the sun's core shouldn't get close enough to fuse because they repel each other electrically. Thanks to quantum tunneling, however, some protons penetrate the energy barrier, allowing fusion to happen at the rates we observe. Without quantum mechanics, the sun would be dark and cold. In the field of condensed matter physics, quantum mechanics explains why materials have their unique properties. Superconductivity, for example, is a quantum phenomenon where electrons pair up and flow without resistance through a material at low temperatures. Similarly, superfluidity, where liquid helium flows without viscosity, arises from quantum effects acting on large scales, creating states of matter that seem to defy common sense. One of the most mysterious yet experimentally supported facts is the Casimir effect. When two uncharged, parallel metal plates are placed very close together in a vacuum, they experience an attractive force, not because of any direct interaction, but because quantum fluctuations of the vacuum itself are suppressed between them. This shows that even empty space is not truly empty, it teems with restless quantum activity. Quantum mechanics also governs blackbody radiation, explaining why objects emit light as they're heated and why the spectrum of that light depends on temperature. This was historically one of the first clues that classical physics was incomplete. The so-called ultraviolet catastrophe predicted infinite energy output at short wavelengths, but quantum theory fixed it by showing that energy is emitted in discrete quanta, or photons. A striking fact from particle physics is the phenomenon of quantum vacuum fluctuations, where particle-antiparticle pairs spontaneously pop in and out of existence even in empty space. Though fleeting, these virtual particles have measurable effects, such as slightly shifting the energy levels of electrons in atoms, a phenomenon called the Lamb shift, and influencing the fine structure of the universe itself. In quantum optics, experiments with single photons have demonstrated wave-particle duality with astonishing clarity. When a single photon is sent through a double-slit apparatus, it produces an interference pattern, acting like a wave, but when measured, it behaves like a particle. The fact that this happens even when photons pass one at a time underscores the deeply non-classical nature of the quantum world. Finally, quantum mechanics is at the heart of the emerging field of quantum metrology, which aims to achieve measurements at the absolute limits allowed by nature. Using techniques like squeezed light and entangled states, scientists are pushing the boundaries of how precisely we can measure time, gravity, and other fundamental quantities. This work promises transformative advances in navigation, fundamental physics, and even the search for gravitational waves. One of the most exciting frontiers today is quantum computing, where researchers are harnessing the strange rules of superposition and entanglement to perform calculations beyond the reach of classical computers. For example, quantum algorithms like Shor's algorithm can factor large numbers exponentially faster than the best-known classical algorithms, a breakthrough that could one day revolutionize cryptography and cybersecurity. Another algorithm, Grover's algorithm, offers quadratic speedup for searching unsorted databases, showing that even tasks with no obvious quantum advantage can benefit. In quantum communication, scientists have already achieved unbreakable encryption using quantum key distribution, QKD. This technique relies on the no-cloning theorem and the fact that any attempt to intercept or measure quantum data disturbs it, revealing eavesdropping attempts. Countries like China have already launched quantum communication satellites to test long-distance QKD, laying the groundwork for a global quantum internet. An astonishing scientific fact is that quantum entanglement has been tested over enormous distances. Experiments have successfully entangled particles over hundreds of kilometers. In 2017, Chinese researchers used the Mishia satellite to distribute entangled photon pairs between two ground stations over 1,200 kilometers apart, smashing previous records and proving that entanglement is robust even across space. In biology, quantum mechanics may play a role in processes like photosynthesis. Experiments suggest that quantum coherence, where particles maintain a shared phase relationship, may help plants and bacteria transfer energy with near-perfect efficiency, guiding energy through molecular networks like a quantum walk. This discovery hints that nature may have evolved to exploit quantum effects long before humans even knew they existed. Another fascinating example is quantum annealing, a computing approach that uses quantum tunneling to escape local energy minima and find the global minimum of a complex problem. Companies like D-Wave have built early quantum annealers, exploring their use in optimization problems from logistics to machine learning, although they are not yet true universal quantum computers. In the search for dark matter and fundamental physics, quantum sensors are becoming indispensable. Atomic clocks, for instance, are now so precise that they can detect minuscule differences in time caused by variations in gravitational potential, helping test general relativity and search for exotic physics. Quantum sensors based on ultra-cold atoms or nitrogen vacancy centers in diamonds are also being deployed to hunt for dark matter or tiny distortions in spacetime. One of the most profound implications of quantum theory is that it challenges our understanding of information itself. The discovery of the black hole information paradox, the question of whether information is lost when matter falls into a black hole, has sparked intense debate and pushed physicists to explore the deep links between quantum mechanics, gravity, and spacetime. Recent proposals, like the holographic principle, suggest that all the information in a volume of space might be encoded on its boundary, hinting at a radically new picture of reality. At the philosophical level, quantum mechanics forces us to rethink the very nature of reality. Unlike classical physics, where objects have definite properties whether or not we observe them, quantum theory suggests that certain properties, like position, momentum, or spin, don't have definite values until they are measured. This raises profound questions about what it means to exist before observation and has fueled debates about whether reality is fundamentally objective or participatory. The famous measurement problem is one of the deepest puzzles in physics. Why does the act of measurement collapse a quantum superposition into a definite outcome? Different interpretations try to explain this. The Copenhagen interpretation says that probabilities are fundamental, while the many worlds interpretation proposes that all possible outcomes happen, splitting the universe into countless parallel branches. Other interpretations, like Bohmian mechanics, suggest hidden variables guide particles deterministically, while objective collapse theories propose that wave functions collapse spontaneously, independent of observation. Another profound quantum insight comes from quantum field theory, QFT, which unites quantum mechanics with special relativity. In QFT, particles are not fundamental objects but excitations of underlying fields that pervade all of space. This framework has led to the discovery of the Higgs boson, predicted antimatter, and explained the forces of nature with stunning precision, yet it also suggests that the vacuum itself is an active, fluctuating medium rather than a true emptiness. Entanglement has also taken on a surprising role in modern theoretical physics. Some researchers, including Juan Meldacena and Leonard Susskind, have proposed that spacetime itself might emerge from quantum entanglement, a radical idea that suggests geometry and gravity arise from the connectivity of quantum information. This hints at a deep link between quantum mechanics and general relativity, the two pillars of modern physics that have long resisted unification. Black holes offer an arena where these mysteries collide. Hawking radiation, a quantum process, allows black holes to slowly evaporate, but it also raises the question of whether the information about what fell in is lost forever, potentially violating a core rule of quantum mechanics. Recent breakthroughs suggest that information might be preserved, encoded in subtle correlations among Hawking radiation particles, pointing toward an eventual reconciliation of quantum mechanics with gravity. Another mind-expanding area is quantum cosmology, which applies quantum principles to the entire universe. Models like the Hartle-Hawking no-boundary proposal suggest the universe may have spontaneously emerged from a quantum fluctuation, without a sharp beginning or before the Big Bang. This pushes physics to its limits, challenging our understanding of time, causality, and the origins of existence. Even in the world of everyday materials, quantum mechanics has led to the discovery of exotic phases of matter, like topological insulators, quantum Hall states, and time crystals. These states don't fit into classical categories of solid, liquid, or gas. They rely on quantum effects to stabilize entirely new forms of order, with potential applications in fault-tolerant quantum computing and new technologies we can barely imagine. Another captivating frontier is the use of quantum entanglement in quantum gravity experiments. Researchers are exploring whether gravitational fields themselves can become entangled, testing if gravity is fundamentally quantum. Recent proposals suggest that if two tiny masses are placed into quantum superpositions and their gravitational fields interact, observing entanglement between them could provide evidence that gravity must have a quantum nature. Such experiments, though technically challenging, are now moving from theory toward laboratory tests. In the domain of quantum timekeeping, atomic clocks have reached such extraordinary precision that they can detect the tiniest variations in time caused by changes in altitude. Even lifting a clock just a few centimeters alters its ticking rate due to general relativity. This unprecedented precision not only helps in global navigation systems like GPS but also allows scientists to probe whether fundamental constants, like the fine structure constant, change over time or across the universe. An astonishing fact is that quantum fluctuations may prevent the universe from total collapse. Some theoretical models suggest that quantum effects in the vacuum could exert a kind of quantum pressure that opposes gravitational collapse, possibly influencing the fate of the universe itself. While still speculative, this hints at quantum mechanics playing a role not just at the micro scale, but at the ultimate cosmic scale. In quantum thermodynamics, scientists are uncovering how classical thermodynamic laws emerge from quantum systems. For example, they're exploring how entropy, a measure of disorder, works when applied to quantum states and how energy flows in nanoscale machines. This research is pushing the boundaries of what we know about heat, work, and information, with potential implications for ultra-efficient energy harvesting in computing. Quantum biology is also an emerging field, examining whether living systems harness quantum effects to function. Apart from photosynthesis, researchers are investigating whether birds use quantum entanglement in their magnetic sense to navigate using Earth's magnetic field, or whether enzymes exploit tunneling to accelerate reactions. If confirmed, this would suggest that evolution has tapped into quantum resources billions of years before we began to understand them. In quantum foundations, scientists are exploring the limits of reality with delayed choice and quantum eraser experiments. These show that choices made in the present can seemingly influence the behavior of particles in the past, at least in terms of how we describe their behavior. While no causality is violated, these experiments challenge our classical notions of time and underscore the strange non-locality of quantum systems. And in the search for the theory of everything, quantum mechanics remains the biggest piece of the puzzle. Any attempt to unify the standard model of particle physics with general relativity, such as string theory or loop quantum gravity, must reconcile quantum rules with the smooth geometry of spacetime. Quantum mechanics, with all its strangeness, remains central to our quest to understand the deepest laws of nature. One remarkable effect is the quantum Zeno effect, which shows that the mere act of frequent observation can freeze the evolution of a quantum system. Named after the ancient philosopher Zeno, whose paradoxes question motion and change, this effect demonstrates that rapidly repeated measurements can effectively halt the natural transitions of a system, like keeping an excited atom from decaying just by continually checking on it. This challenges our classical intuitions about time and change. Another profound thought experiment is Wigner's friend, which extends the Schrödinger's cat scenario. In this setup, a friend inside a lab measures a quantum system, while an outside observer, Wigner, treats the entire lab, including the friend, as a quantum system in superposition. This leads to deep puzzles about the role of consciousness and the limits of quantum description. Are both observers right, or does reality split depending on the observer? This touches on the very foundations of what measurement and observation mean in quantum theory. In quantum teleportation, one of the most futuristic-sounding technologies, scientists are able to transmit the exact quantum state of a particle, like a photon or electron, from one location to another, using entanglement and classical communication. This isn't teleportation of matter, but rather of information, and it's already being demonstrated in labs, with applications for future quantum networks and secure communication. A surprising application of quantum mechanics is in quantum radar. Unlike classical radar, which sends out electromagnetic waves and measures reflections, quantum radar can use entangled photons to detect objects with lower signal levels and better noise resistance. This could revolutionize detection technologies, particularly in cluttered or stealthy environments. Quantum mechanics also revolutionizes our understanding of information and entropy. According to the field of quantum information theory, the maximum amount of information you can store in a region of space is proportional not to its volume but to its surface area, a concept deeply linked to the holographic principle. This principle suggests that all the information about a 3D region can be encoded on its 2D boundary, leading to radical proposals about the nature of spacetime and black holes. Recent breakthroughs in quantum technology include time crystals, exotic systems that exhibit a repeating structure not just in space, like ordinary crystals, but in time. These systems break time translation symmetry, behaving in ways once thought impossible, and they could open new paths in quantum computing and material science. Another stunning discovery is the realization that quantum entanglement may be the fabric of spacetime itself. Theoretical physicists have proposed that the geometric structure of spacetime might emerge from underlying patterns of quantum entanglement, meaning that without entanglement, space and time as we know them might not even exist. Finally, quantum experiments continue to push into macroscopic scales. Scientists are working to put larger and larger objects, even molecules and tiny mechanical devices, into superposition states. Successfully doing so would further blur the boundary between the quantum and classical worlds and help probe whether quantum mechanics truly governs everything or whether some boundary, perhaps caused by gravity, eventually limits quantum effects. One of the biggest puzzles is the measurement problem. While the Schrödinger equation predicts smooth, deterministic evolution of quantum states, we only ever observe definite outcomes, a particle detected here, not everywhere. What causes the collapse of the wave function into a specific result? Is it the observer's consciousness, environmental decoherence, hidden variables, or some as yet unknown process? This is one of the most hotly debated questions in the philosophy of physics. Closely related is the question of quantum gravity. How can we reconcile the smooth, geometric description of spacetime from general relativity with the probabilistic, non-deterministic world of quantum mechanics? Attempts like string theory and loop quantum gravity try to bridge this gap, but so far no experiment has confirmed a complete theory. Understanding quantum gravity may explain black hole interiors, the Big Bang, and even why time flows forward. The black hole information paradox is another key mystery. If a black hole evaporates through Hawking radiation, what happens to the information about what fell in? According to quantum mechanics, information cannot be destroyed, yet general relativity seems to suggest otherwise. Recent developments involving holography, entanglement, and soft hair around black holes are offering clues, but the full resolution is still unknown. A cutting-edge question is whether quantum mechanics is truly complete. Are there hidden variables, deeper layers of reality that explain the randomness of quantum events? Bell's theorem and decades of experiments suggest no local hidden variable theory can match quantum predictions, but some researchers continue to explore non-local or superdeterministic models. The idea of quantum contextuality also challenges our understanding of reality. Contextuality means that the outcome of a measurement depends not just on the system but on how the measurement is set up, the broader experimental context. This has been experimentally confirmed and suggests that the universe is even stranger than non-locality alone implies. On the technological frontier, one of the great challenges is to scale quantum computing to useful sizes. While today's quantum processors have tens or hundreds of qubits, they still struggle with noise, decoherence, and error correction. Achieving quantum supremacy, solving tasks beyond classical machines, has already happened in narrow cases, but general-purpose quantum computing remains a massive challenge that could transform industries from pharmaceuticals to finance. Another exciting application is the quantum internet, a global network based on quantum principles, enabling ultra-secure communication, distributed quantum computing, and fundamental tests of physics. Early quantum communication links have already been demonstrated over hundreds of kilometers, and the first prototype networks are under development. Finally, at the edge of theory and speculation, some physicists wonder whether quantum mechanics hints at a multiverse. In the many worlds interpretation, every quantum event splits the universe into parallel branches, each realizing a different outcome. If true, this would mean an unimaginably vast number of parallel universes coexist alongside our own, though whether this idea is testable remains an open debate. In the end, quantum mechanics stands as one of humanity's greatest intellectual achievements, a theory that reshaped our understanding of nature at the deepest level. It challenges our assumptions about reality, causality, and even the flow of time, inviting us into a universe that is far stranger and more beautiful than classical physics ever imagined. From the tiniest particles to the vast structure of the cosmos, quantum principles are woven into the fabric of existence, shaping everything from the stars above to the technology in our pockets. As we continue to explore its mysteries, from quantum gravity to computing, from biology to cosmology, we stand on the edge of discoveries that may once again revolutionize science and philosophy alike. Quantum mechanics reminds us that the universe is not just a cold, predictable machine but a realm of endless wonder, where uncertainty and possibility dance together at the heart of reality. And in seeking to understand it, we not only unlock the secrets of the cosmos but also deepen our understanding of ourselves as curious, questioning creatures in a quantum world.